Hey, what's going on, everyone? Welcome back to our mechanics of materials sequence. And in this video, we're going to address, or we're going to talk about shearing stress. And hopefully, by the end of this video, you will be able to define shear stress and average shearing stress, and then take a look at some simple connections, draw the free body diagram of those, and identify what is single shear and double shear. And then lastly, we'll go talk about what direct and indirect shear are, and that way we know which formulas apply or are appropriate in each case. Um, but here, just to get started off, in terms of shear stress, whenever I think of shear stress, it's I think of something sliding by something else. So the image I have in my head is a book, right? If a book is resting on a table and it's attached to that table right here, and I put my hand on top of the book and I force it, I push alongside of it, I know that this thing will deform like this right here. It'll essentially shear right here. And if all the pages were bonded together, uh, I would have shear stress develop in between each layer within the material or within the book between the pages. And that would be kind of like shear stress, right? Other things you might think of are scissors whenever they slide past each other to cut something, or flow, even fluid flow, and especially where the fluid touches the structure that's containing the fluid, like a pipe or like a riverbank, I guess, the riverbank and the fluid right there. There's some shearing action going on where the fluid is sliding by the body or the structure. Okay, so fluid flow right here. So that's what I think of, and officially it's whenever you have a force that's causing your body, the structure, to slide by each other. And I'm rubbing my hands right now, but you can't see it. I'm rubbing my hands together, and that's causing shearing, shearing action going on there too. Um, but the thing I think of here, let's take an example here. Let's take a connection here. So here I pre-drew if you can imagine, a bolted connection with two plates here, or one, two, three plates here, and then let's say I have some force. I'll call that P here. And if this whole thing is in equilibrium right here, this connection, I know that each of these forces here is going to be P over 2. Okay, on this plate right here. And then if I isolate and I cut right here, if I were able to cut and I isolated this one center plate right here, I would see that I have this force P here, and here, for this to be in equilibrium, I have this shear force acting along the area of the bolt, the cross-sectional area of this bolt here, and this would be P over 2. These would be P over 2, and this would be P in equilibrium. So this P over 2 is a shear force acting on the cross section or the surface of my bolt. And if I were to look here, if I look down at this bolt right here, what I might see is, I would see, if I look at the bolt right here, if I can draw the bolt, bam, and let's say, again, I'm looking down at this bolt right here, right there, and what I would see is that I have this P over 2 acting on the top of it, this P over 2, which, which induces essentially a stress, a shearing stress that's rubbing, if you will, on top of this bolt, okay, or the area of this bolt here. And this right here, this would be my shear stress, tau. We'll call this tau average. This is my shear stress, and I have a diameter of this bolt right here. Okay, diameter of the bolt, I'll call it dB right here. And if I want to calculate the average shear stress, tau average, I'm going to take the shear force over on my bolt divided by the cross-sectional area of the bolt right here, which in this case would be P over 2 divided by the area of the bolt, which would be pi dB squared over 4. Okay, right here, tau average. Now this equation here represents the average shear stress. This is kind of a generic equation for average shear stress, which essentially is the shear force acting on that surface divided by the area. Okay, so we can take this as, if I take the bolt part off, if I take that off, let's see, I erase that right there. So this would be an equation to calculate the average shear stress. Now, one thing you have to note is that this equation assumes that the shear stress on the surface, the shear stress that's acting on top of the surface, is uniform, which it is not. Okay, and this equation usually only works for simple connections or bolts or small areas. Where you don't have a lot of other things going on, but really for and typically in direct shear cases, and this is an example of direct shear, which we'll get into more in a little bit. Okay, so now that we have a feel for what the average shear stress is, let's talk about what simple connections, some simple connections. This right here, this connection here, is called a double shear connection. Double shear. Double shear. And the reason it's called double shear is because it has two planes of shear. One, yeah, I'm doing green. One, oh, can you even see that? No. Let's see here. Can you see that? One plane and two planes of shear here. So that's called a double shear connection. Okay. And the force that's applied here gets distributed over the shear planes, and by equilibrium, each of the shear forces acting over each area of the bolt is P over 2. The For single shear, what's called single shear, as you might be able to imagine, single shear is where you have two plates. And let me draw that real fast. I got here, bam, bam, and then another. Let's put another plate here, like that, and right here. Okay, and so I have two plates here and a bolt going through that plate. Let's put it right here using my straight edge, having nice clean drawings. Hopefully they're clean. Okay, right here, bam. Oh, we'll make that a little bit longer for the bolt and nut. Okay, bam. All right, and here, and so if I have this single shear right here, and I have this force P by equilibrium, I know each of these forces to transfer, to transfer the force in this plate or bar across to the other bar connected to it. I have to, it's all going to be P. The normal force is going to be P in each. And if I make a cut right here, if I make a cut, let's see what I used red before. So if I make a cut and isolate one of these plates, so that I have, let's say I isolate the bottom plate right here, and bam, like this. I make a cut through the bolt. I have here the bolted connection. Let's say it's sticking out right here, like this. Here's the nut holding it in place, and here is that surface right here of the bolt, and I know that the shear force acting across here is going to be equal to P. I have, because of equilibrium, this is P right here, and so here the average shear stress here, tau, equal to V divided by A, would be P divided by the area of the bolt, the cross-sectional area of the bolt here, or tau average. Okay, and this is single shear because I have only one plane of shear in this connection. And I can do the same for glued surfaces. So if I had, let's say, two plates, let's see if I can draw this in 3D a little bit. Yeah, I'm going to kind of forego my eraser. If I had this, let's see right here. Yeah, that's not bad. Okay, not bad. Maybe all right here. But if I had maybe glued on these two things together, these two plates or wood pieces, whatever. If I glue it on, I isolate just one. Let's see, can I isolate just one? I need another page. And I isolate just one, then, and I look at one right here. So if I look at the bottom piece right here, okay, and I have bam, bam right here. And let's say that I had a force P and a force P acting on here, then if this is my glued area right here, this is area of the gluing right here, and if I have my free body diagram but just the bottom piece right here, I know that this V, the shear force acting over the glued surface, is equal to P right here, and then the average shear stress, tau average, for this would also be V divided by area, the glued area, the area of the glue right here, and this would just be V divided by A, P divided by A, because V equals P. And That's how I would calculate the average shear stress, and I can figure out how much glue area I need to make sure I can carry this load if I have, the shear strength of the glue. Okay, and this is the basic idea behind bolted connections and in steel construction and something you might find in ASME or AISC codes. And the formulas are basically the same. There's this idea of tau average equal to V over A, except there's some code modifications depending on the surface or the materials that are used, and other ways besides just failing in the bolt. There's other ways that a connection can fail, but that we're not going to address that here. Um, but what we want to get into next now is really just as we move on here, we've talked about shear stress, we've talked about simple or single shear, simple connections, and single shear and double shear. And now really, we want to be able to differentiate between direct and indirect shear. Now, everything that we've done here, if I go back up, respond, okay. If I go back up right here, this double shear and single shear, this is an example of direct shear. Okay, direct shear because the applied load is causing the stress, the shear stress directly. Okay, it's right here. Um, in terms of direct shear, let's see, direct shear. Uh, okay, so the applied load causes, shear stress by direct action or directly. Let's see, typically, not all the time, but typically that shearing surface, shearing surface is parallel to the applied load. And other examples might be like a hole puncher. I'm sure all of you have worked with a paper hole puncher, and that's direct shear. That's causing shear stress. And the idea is the same behind punching holes through metal plates. Okay, so you punch a hole through a metal plate, you got that's also direct shear. There are some direct shear tests for wood, like wood specimens, to measure transverse shear. But anyway, I think the hole punching thing is more relevant to you. Some examples of indirect shear, it would be the shear stress caused by axial loading, torsion, bending, okay, or bending right here. So if I think of something, let's see, like if I think of a traffic sign or a beam that's bending, and and a beam that's bending, I'm going to have shear forces develop. Um, if I have a beam, let's say here, like this, here, and here, like that, and I apply a concentrated load here, I'm going to have shear forces developing throughout the beam. If I make a cut, I'm going to see shear forces and shear stresses in between the layers of the beam, um, and as well as in the vertical planes as well. And then if I think of like maybe something more relevant, like a traffic sign that you look at. So if I can draw a traffic sign, looks like this here. Here's my traffic sign right here, and I'll fix it here, and I have this, bam, like this right here. So I've got lots of things going on in the traffic sign. I've got the weight of the sign pulling it down this way. I've got the wind that's blowing into it and causing this whole thing to twist. And that also causes shear stresses within the pole that's holding it. Okay, so I have lots of things going on here that can, and also this load right here causes bending, causes a moment reaction here that will also have shear stresses that are going to develop within the beam or the cantilever that's holding up the sign. So these are indirect shear and then direct shear. So hopefully this video was helpful in giving you a little bit of an introduction to shear stress and calculating the average shear stress. We'll do some examples in the next video. All right, talk to you later. Thanks.